All right, so you saw that a molecule, last time we saw that a molecule, if it's on the surface, there's a net force on it downwards, so you can think of it as a stretched spring. This molecule on the surface is being pulled down, okay? So it costs you energy to put a molecule on the surface, okay? So if you have a bunch of water like this, okay? Well, let's say if you have a drop of water, this drop of water will always take a spherical shape, because for a spherical shape has the least surface area. And what does that mean? When it has the least surface area, that's the least number of molecules on the surface. Okay? So it costs you the least amount of energy for that shape. All right, so a liquid surface, because of these cohesive forces, behaves like a stretched rubber band, rubber sheet. Okay? And that's surface tension. Okay? And that's what makes this kind of stuff possible. Bugs can walk on the surface of water as long as they do not break the surface of water. Okay? So it's like a trampoline. As long as your feet don't go through the surface, if your feet are on the surface, you can walk on the trampoline. Okay? If you break the surface, now you can't do that anymore. Okay, so that's surface tension, and this is going to be important for us. Okay? All right, so here are surface tensions of various fluids. Here's blood plasma, has the surface tension units are Newton per meter. Okay? As that, the surface tension of water is 0.706, 0.072, and so on. Okay, look at that. Mercury, the surface tension of mercury is 6 times that of water, and we'll talk about that. So the greater the surface tension, the greater the attractive forces between the molecules. Okay, and that'll be important. By the way, I've changed this formula slightly in the notes, so if you have the old notes, you might want to correct that. Okay, so here's how surface tension is measured. So if, for instance, if you want to measure the surface tension of water or soapy water or whatever, by the way, soapy water, see, the surface tension of soapy water is half that of pure water. Okay, so soap is a surfactant which reduces the surface tension. Okay, so any material that reduces the surface tension of a fluid is called a surfactant. Okay, and that'll be important for breathing. So we'll talk about that in a second. All right. So here's how surface tension is measured. So if you have soapy water, make a soap film around this piece of wire and pull this wire. The greater the surface tension, the more force you need to pull this thing. Okay? And surface tension, denoted by gamma, is the force that you apply. And this, okay, so every film all films have 2 surfaces. So I'm going to sort of draw a side view of the film. So when you're pulling the film, you're pulling both the films. Okay, so that's why it's the force you apply divided by the length of the film, which is 2L, and that's the change I made in the formula. All right. So again, what I want you to remember is, you have the surface of any liquid. The surface of any liquid is like a stretched rubber sheet. Okay. Greater the surface tension, greater the tension in this sheet. Okay. Greater the tension in the surface tension, heavier the bugs you can lift. Okay, that's what that would mean. All right, so here is what is relevant for us. Okay, so if you have a bubble, okay, so here's a balloon made of rubber. And this balloon, what it does is it increases the pressure inside in the air. Okay. The amount by which it increases the pressure is 4 times the surface tension divided by the radius of the bubble. All right, so which bubble has greater pressure? The big one or the small one? Okay, so the big one has a greater radius and it has a smaller pressure. Okay, so if you connect these two bubbles, the pressure inside the smaller bubble is greater, so air will flow from here to there. Okay, so if you connect these two bubbles, this air will flow from here to there, and this guy will go to zero, and all the air will end up there. So let me show you a little simulation on that. Okay, so it is counterintuitive. Okay, so
Illustration here, and I'm not sure where you might put this in the curriculum. One thing is certainly with gases, it involves balloons, but it's just a good little eye-opener, and it's a good way of showing how math really has some power in the making predictions. So I have two balloons, and if you're wondering, this setup can be done with rubber stoppers and tubing and clamp, but this is a little different. This is the top of a little
all right. So we have a small balloon and a big balloon, okay? And of course, for this to work, you have to have the same rubber material, okay? And hopefully in a bag, there's the same rubber material, okay?
What's going to happen when I open the passageway between these two balloons? Okay, I have to pop this open and pop that open. And when I first saw this done, I had kind of an obvious prediction. It's only fair that the balloon should even out, right? This is unfair. Well, let's see if that's true. So we're going to open this side, and now we're going to open this side. The rich get richer. Not at all fair.
Okay, so you saw that the smaller radius, okay, the smaller radius has greater pressure. The air inside there was at a greater pressure, and fluid flows from a higher pressure to lower pressure.
So which side has the greater pressure? The big one? I thought the smaller the radius, the higher the
Okay, the smaller the radius, the greater the pressure.
So the big balloon does have the more pressure.
No, this guy has the smaller radius. It's inversely related. So this has higher pressure, and the pressure here is lower. So fluid flows from a higher pressure to lower pressure. Okay? All right. So this is important for us. So for instance, all right, so I'm going to draw, so here's your air wave. Okay. So obviously our lungs are not one big balloon. Why aren't our lungs one big balloon? You guys, all right, so we will talk about diffusion next time. Diffusion is so let's say you have a glass of water, and I drop one drop of ink. That ink will diffuse. But this diffusion process happens very slowly, so the ink doesn't travel too far. So just like that, oxygen in air diffuses into your blood vessels, and that diffusion process, so how long does that air have to get into your blood? The oxygen in the air, how long does it have to get into your blood? About a second. So it can't travel too far. So that's why what we do is we have tiny air sacs called alveoli, which are surrounded by blood vessels. Okay. So your lungs are broken up into tiny alveoli like grapes in a branch. Okay. So keep that in mind. All right. So what that means is, where are we? Okay, so your alveoli are tiny bubbles, and there's a increased pressure in them. Okay, so we'll come to that. Okay, so adult lungs contain about 300 million tiny mucus-lined sacs called alveoli. So each lung has that. The exchange of gases such as carbon dioxide and oxygen with blood occurs in these sacs via diffusion. And diffusion, when you're exchanging stuff via diffusion, you can't travel too far in about a second. Okay, so that. And the large number of sacs increases, and here's another thing it does. The large number of sacs increases the surface area available for interchange. Okay, so if this were the lungs, and if you make, okay, if you break up into tiny alveoli and then surround these alveoli with blood vessels, then you have larger surface area to exchange.
Are you right, or making a picture, it's not showing?
All right, so I guess I got to choose a different color. Okay, there you go. You break your lungs into tiny alveoli and then surround these alveoli with blood vessels. Now you have larger surface area to exchange the gases with the blood. Okay. All right. Now, before we do these next two slides, let's go over this problem so we will understand breathing. Okay, how breathing happens. All right. So you saw that if you have a bubble, the pressure inside the bubble increases by this much. Okay, so R is the radius of the bubble, and gamma is the surface tension. All right, so now I'm going to just give you the punchline on these, and these numbers will be important. So here's a water bubble, and it's 2 times 200th of a centimeter. The radius of the bubble is 200th of a centimeter. Okay, and 0.1 centimeter is a millimeter. So this radius is 0.2 millimeters. Okay. This radius is 0.2 millimeters. Here's another bubble, a water bubble 5 times larger is 10 to the minus 1 centimeter. So the larger bubble has a radius of 1 millimeter. Okay, the reason we are considering this is the following. So this is the normal size of your alveoli. In emphysema patients, what happens is, in emphysema patients, several alveoli combine and they become a bigger alveoli. They become that big. Okay? And why is that relevant? Because if the radius becomes bigger, you guys following this? What happens to the pressure inside? It lowers. If the pressure lowers inside the alveoli, they have trouble pushing out the air. They have trouble breathing. So we'll come to that. Okay? All right, so this is the normal size of alveoli. This is a bigger bubble, and the pressure inside will be smaller, and we'll look at the numbers. And then the third example is a bubble of water. Again, the radius is the same, 0.2 millimeters, with a surfactant that reduces the surface tension to that. A surfactant reduces this number. If you reduce that number, the pressure decreases. Okay. All right. So we'll come to that. All right. So the first one, part A, I'm going to write the numbers down. And again, you don't have to know every step of the details, but I want you to know the results. Okay. So the first is a water bubble. That's the size. The radius is that's the size of the alveoli. Okay. So radius is 0.2 millimeters. Gamma, the surface tension, it's water. The surface tension is, and the surface tension of water is 0.072 Newton per meter. 0.072 Newton per meter. And using this formula, so this is the formula we've calculated. Okay. And using this formula, the pressure is calculated, and the pressure is, so it goes through all the calculation, and the pressure is, so part A, 10.8 millimeters of mercury. Okay, so that's the pressure, 10.8 millimeters of mercury. For part B, okay, so there you go with the calculation. The radius is 1 millimeter. Okay. So this is what happened for emphysema patients. Several of the alveoli have coalesced. They become a large bubble. Okay. And because they've become a large bubble, the pressure decreases. Okay. So, and and gamma is they're using the same gamma. Gamma is 0.072 Newton per meter, and the pressure reduces to 2.1 millimeters of mercury. 16 millimeters of mercury. Part C, radius is 0.2 millimeters, so the same size radius. Gamma is reduced. This is with a surfactant. Calculate and the surfactant is that, and that's what happens in your alveoli. Your alveoli has surfactants, and the surface tension is reduced, so it's 0.037 Newton meter. And so the pressure inside is, and the pressure calculation is there, 5.55 millimeters of mercury. Okay, so I want you to remember that. Okay, now let's see how breathing works. All right, so let's, and this will illustrate a few diseases as well. Okay. All right, so now we'll do the following. So here's your nose and stuff like that. And all I'm going to draw is a path. So there's many branches and stuff. And we'll draw a tiny alveoli. Okay, well, I won't draw it too tiny. So there's your alveoli. Okay, now to move a fluid from one end to another end, you have to have higher pressure and lower pressure for the fluid to move this way. Okay. All right, you want to breathe in. What is the pressure here outside? 1 atmosphere. The pressure here is at 1 atmosphere. Does that pressure change? No. So if you want to breathe in, if you want to breathe in, what do you have to do? You have to lower the pressure here. Okay? And when you want to breathe out, what do you have to do? You have to increase the pressure here. Okay? You have to, so what you're doing is you're changing the pressure in the alveoli. The pressure outside is not changing. So when you want to breathe in, you have to decrease the pressure below atmospheric pressure. And when you want to breathe out, you have to increase the pressure above atmospheric pressure. Okay, so that's how you're going to breathe. Okay. Well, are you going to change the size of the alveoli? So here's what you do. So so here is the thoracic cavity. What you're doing is you're changing the size of the thoracic cavity. That's how you're changing the pressure inside the alveoli. Okay? So when you want to breathe in, your diaphragm goes down, and the pressure inside the thoracic cavity changes. Okay. And here are the numbers from the next chapter. Again, you'll see this. So the interthoracic cavity, and this pressure is in millimeters of mercury. Okay. So it changes between -4 and -8 millimeters of mercury. Okay. So let's go back to our thing. All right. So in our example, so there's for example C. All right. So there's the size of the alveoli, and for that surface tension, there's the pressure, 5.5 millimeters of mercury. Okay, so let's go back here. All right, so in everything, okay, by the way, all the pressures are gauge pressure. So this at gauge pressure here, it's 0 millimeters of mercury. Gauge pressure is absolute pressure minus atmospheric pressure. Okay, so this is, the pressure here is 0 millimeters of mercury. Okay. All right, so if you have 0 millimeters of mercury here, then the pressure would be the same and no flow will happen. For flow to happen, this has to become negative pressure. Okay? All right. This guy is providing 5.5 millimeters of mercury. Okay? And remember, the interthoracic pressure changes between -8 and -4 millimeters of mercury. Okay. So when you're breathing in, your lungs have expanded, and the pressure inside your cavity, inside your interthoracic cavity, is -8 millimeters. 5.5 -8, you get a total net pressure of -3 millimeters of mercury, and you have air flowing in. When you want to breathe out, you collapse your diaphragm. The pressure in the interthoracic cavity is -4 millimeters of mercury. 5 minus 4 is 1 plus 1 millimeters of mercury. The pressure is higher, air flows out. Do you guys understand that? Okay. So again, to summarize this, okay, when you want to breathe in, the pressure inside the alveoli needs to be less than 1 atmosphere and air will flow in. When you want to breathe out, the pressure inside the alveoli needs to be greater than the atmospheric pressure and the air will flow out. And the way you control that is by changing the pressure in the interthoracic cavity. Okay, so here's the pressure, 5 millimeter of mercury because of the walls, elastic walls. Okay. And when the outside pressure is -8, 5 minus 8 is -3.3, so -3 millimeters of mercury is the pressure here, and air will come in. When you breathe out and when your diaphragm moves up, the interthoracic pressure is -4 millimeters of mercury. This -4 is 1.5 plus 1.5 pressure. This pressure is higher and air will move up. Now let's look at the problems. Okay, so let's look at what happens with emphysema patients. What happened with emphysema patients? With emphysema patients, many of the alveoli coalesced, the radius increased, the alveoli became big, the pressure inside the alveoli was only 2.1 millimeters. Okay? So let's go back to our diagram. Now for emphysema patients, this is 2.1 millimeters. Okay, so here's an emphysema patient trying to breathe out. You collapse your diaphragm. This is still -4 millimeters. 2 minus 4, this is still negative pressure. You're not able to push out air. Did you guys understand that? All right. Now we'll talk about another disease. Okay. So emphysema patients have hard time pushing out air, hard time clearing your alveoli. Okay. And so we sort of help them out with, I guess, having them breathe pure oxygen and stuff like that. Okay. And maybe they might reduce the pressure here. I don't know what the machine does. Okay, so now let's look at another disease. Here's a disease that, so sometimes surface tension in alveoli can be too large. Okay, so surface tension, here's the expression for pressure, gamma divided by R. So if this is too large, the pressure inside is too large in the alveoli, and then it's harder to breathe in. It's harder to inflate the alveoli. Okay, so sometimes surface tension in the alveoli can be too large, making them difficult to inflate. Such a problem called respiratory distress syndrome occurs in premature infants and can be fatal. Normally, a substance called a surfactant reduces the surface tension of the mucus lining of the alveoli so that they can be inflated properly. Some infants lack surfactants. Okay, so essentially the surface tension is the surface tension of water and can only breathe with great effort. All right, so going back to this. Okay, so in some newborns, the surface tension is higher. So this is the normal surface tension in your and my alveoli. In some infants, because they lack the surfactants, the surface tension is that. There's the size of the alveoli, and there's the pressure inside the alveoli. All right, so now let's go back to this diagram. So that is 11 millimeters of mercury. Okay, so why did this happen? So these newborn children lack surfactants. The surface tension is too high. This number is too high. The pressure is too high. There is the pressure. Okay. Now let's say they try to breathe in. So they expand their diaphragm, they expand their thoracic cavity. There's the pressure, minus 8 millimeters. 11 minus 8, that's still plus 3. Air won't flow in. They can't inflate, they can't breathe. So how do you fix that? Okay, as they grow, they get surfactants in their alveoli. So till then, you have to force air in. Okay. That's a problem. So now here's another problem that you guys are aware of. So here's the normal pressure for normal healthy humans. Okay, you guys have heard of collapsed lungs? What does a collapsed lung mean? When does it happen? So this thoracic cavity is maintaining negative pressure, meaning the pressure is lower than atmospheric pressure. So it's like a vacuum chamber. Okay, let's get into an accident and puncture this. Okay, when you puncture the thoracic cavity, now the pressure is greater than the outside pressure, so this will collapse. All the air will move up and your lungs will collapse. Okay? So this vacuum partial vacuum is what is letting you breathe. Okay? So that's a sealed chamber. All right, so there was a lot going on there. I hope you understood that. Okay, so in this breathing mechanism, something goes wrong, and in diseases, okay. In emphysema, what has happened? The radius of the alveoli has increased. Several alveoli have coalesced, and the radius is increased. in some newborn infants, the surface tension is too high because of lack of surfactants. Okay? And that causes a problem. Okay, so again, the surface tension of pure water is that, and when you add surfactants, this is the normal surface tension in your body. Okay. All right, so that's what we've talked about here. Okay, so again, this expression tells you what is the excess pressure in a, let's say in a bubble of radius r and surface tension gamma. Yeah. So we learned why do we have alveoli, because air is exchanged via diffusion, oxygen and carbon dioxide are exchanged via diffusion, and via diffusion you can only transport small distances in small time. So it's a dual purpose. You're increasing the surface area, so blood vessels, you have larger surface area to exchange material through. And in addition, via diffusion, you can only exchange over small distances. Okay, so, and we learned what kind of problems you'll have if surface tension is not in normal range, and if what kind of problems you'll have if radius is not in normal range. Okay. All right, so a surfactant or surfactant agent is a substance that lowers the surface tension of a liquid. So soap does that, for instance. Okay, soap is a surfactant. Okay, so this diagram shows you in an emphysema patient, the alveoli have coalesced and gets bigger. Okay, so in a victim of emphysema, several alveoli coalesce in people suffering from emphysema to form fewer but larger alveoli. The effect of larger sacs is a reduction of pressure because of their larger radii. This Thursday, we have a otolaryngologist, a surgeon coming to talk. She's a pediatric surgeon, and when the airwaves collapse, what is the kind of stuff they do? So if you want to hear, if you're interested in that, go to the talk this Thursday. Okay. Okay, now we'll talk about adhesive forces. Okay, so cohesive forces, okay, again, to remind you, cohesive forces are forces between like molecules. And adhesive forces are between forces between unlike molecules. Okay, so here's what happens. Okay, so here's water droplets on a wax surface. Okay, so when the cohesive forces are larger than the adhesive forces, then you have droplets forming like that. The surface is not wet as much. When the adhesive forces are larger than cohesive forces, then the water will spread. Okay, so this is an unwaxed surface. All right, the reason we are talking about this is like so. Okay, so this is water in a glass tube. In this glass tube, the forces between water molecules and glass are greater than the forces between the water molecules. And so you have a meniscus forming like this, and this will pull up water. So if you have a capillary tube, okay, the narrower the capillary, the higher water will rise. Okay, so the adhesive forces are responsible for the capillary effect. And you see, the wider the capillary gets, the less the water will rise. So the less that effect is. Okay, so in an extremely wide tube, you'll hardly have any rise. Here's the behavior of mercury in the same set of tubes. So in this capillary, water is rising, mercury, on the other hand, is depressed. Okay, in the case of mercury, the cohesive forces are greater than adhesive forces. Okay. For mercury, the cohesive forces are greater than adhesive forces, and so this surface tension for mercury tells you their cohesive forces are so much larger than for water. Okay. All right, the reason we are talking about this is the following. What we want to know is, okay, so there are trees that are very tall, and how does water get from the roots to the leaves in these tall trees? Yeah. So what are those large trees in California? The redwoods. Okay? And they can be over 200 meters tall. And how does water get from the roots to the? Okay? All right. So this is the capillary effect, the norm, and for water to rise, the adhesive forces have to be greater than cohesive forces. Okay, so high surface tension in liquids tends to inhibit the wetting process, since this is a strong tendency to form drops instead. Water has a relatively large surface tension and does not easily wet many substances such as polyester fibers. Soap, a surfactant, reduces the surface tension of water. It reduces the attractive force between water by coming in between the molecules, okay? Allowing to penetrate and wash away particles of dirt more effectively than plain water. So capillary action is this phenomenon where a fluid rises in a capillary or gets depressed in a capillary. Okay. Capillary action is the rise or fall of a liquid in a tube owing to the interplay of cohesion of the liquid. Cohesion is forces between like molecules to itself and its adhesion to the walls of the tube. Okay. It depressed here because the cohesive forces were greater than adhesive forces. It rose because the adhesion forces were greater than the cohesion forces. Okay. Shown are glass tubes inserted in water and mercury. Water is raised and mercury depressed by capillary action. Okay. So this is the meniscus of the water, this is the meniscus of mercury. This kind of meniscus pulls mercury down, this kind of meniscus pulls the water up. Okay. Water has both smaller cohesive forces and much larger adhesion to glass. Okay. In the water-filled tube, the adhesive forces are stronger than the cohesive forces and pull the water up the walls of the tube. Okay, so the water rises. And mercury, it's the opposite. Mercury has a very high surface tension, very, very large cohesive forces, and forms a surface curve downwards. Okay. So we are interested in how high the water rises. Okay. Ultimately, we want to be able to explain how water gets to the leaves of tall trees, redwood trees, and it's not well understood. It's not completely understood. Okay. The height to which a fluid will rise depends on the surface tension, density of the fluid, and the radius of the capillary. Narrower the capillary, higher the water will rise. Okay, that's what that formula says. Okay. So the question of how tall trees raise sap to their uppermost branches is a controversial one. Okay? The actual mechanism is not well established. Okay? Veins in trees are not small enough to raise sap more than 10 meters. Okay? 10 meters is twice the height of this roof. Okay? So by capillary action, you can only raise up to, let's say, if you go in where the stairway is, from the bottom of the stairway to the top. But you have redwoods that are taller than 2-3 times taller than the tallest buildings in Daytona. Okay? So how does water rise there? It's not just capillary action. It has been suggested that cohesive forces pull up the sap in a long chain. So what they're saying is these water molecules form a chain, and when this water molecule evaporates from the leaves, it's pulling the neighboring molecule and so on. Okay? Again, as one molecule evaporates during transpiration, another is pulled up by the cohesive forces in the chain. Okay? It's not possible to recreate sap behavior under laboratory conditions or to understand the phenomenon theoretically. The question remains open and is under active discussion. I guess. So a simple thing as that, we don't know the answer to. Okay. Okay, we're going to stop here. That ends